from Harishchandra Research Institute, who will be giving this sequence of lectures in this workshop. For the first lecture is about Halasz theorem on mean values of multiplicative functions.
Actually,
over to Surya Ramana.
Right. Thank you so much, Shankar, and thank you so much to all the organizers, several of my friends, all of them, Saurabh, Malaysian, and so on. So thank you very much for having asked me to speak in this course. So what I'm going to do is the whole course is about Halasz theorem. It's 5 lectures. And basically, there's been a lot of work on Halasz theorem, especially making things explicit in the very important papers of Soundarajan, Granville, Harper. That is probably the latest in the series. There are several papers of Soundarajan, Granville on this subject. I do not know if I will be able to get to a point where I can explain what simplifications, advances they have made. So my objective is somewhat, more modest. I want to ensure that I give you a full proof of Halash's theorem, following almost the classical thing as given in Tannenbaum's book, for example, but giving all the details and explaining all the small things that sometimes need to be worked out when you study Tannenbaum's book. So that's my basic objective. I would like to see to it that I managed to present a complete proof of this fundamental result of Halasz. Okay, so that's the goal of these 5 lectures. Now, 2 things I want to caution you about. One is that the internet connection at HRI nowadays is quite unstable. When it works, it's very good. And everything goes on very well, but it can suddenly go off. Okay, so please keep this in mind. As soon as I get the connection back, I'll try to come back. Otherwise, using the phone doesn't seem to work so well. That is one thing I would like to say. And about today's lecture itself, so I have prepared these slides which I will use to give the lecture. But since I cannot see the audience, I may not be able to estimate correctly the speed at which I am supposed to lecture so that everybody is able to follow me. Okay, so I may end up going fast or too slow, one of these things, and probably finishing too early or a little late. So from the next lecture on, I hope to, with some feedback, manage to adjust the slides and the content so that, it fits with the program correctly. Okay. So with these small introductory words, let me just get to the theorem itself. I mean, to the topic of the lecture. So here we are. So this is on Halash's theorem. So first of all, of course, everybody knows these definitions that I am going to recall, but nevertheless, for the sake of completeness and definiteness, let me, recall what is meant by multiplicative functions, which are the main actors in the entire topic. So a function is multiplicative if it's a map from the n star. N star for me is 1, 2, 3 up to infinity. Most people may prefer to call these the natural numbers, but since, as I am fond of saying, 0 was invented in India, I don't see why our natural numbers can't be 0, 1, 2, 3, infinity, and n star is the multiplicative monoid in it, so that's 1, 2, 3, infinity. Okay. Now, a multiplicative function takes the value 1 at 1, and it satisfies this other standard condition that its value on the product of 2 natural numbers here is equal to the product of the values on each of those numbers, provided that those numbers are co-prime. Okay, so this is the definition of a multiplicative function. Please note that f of 1 is equal to 1 is a part of the definition of multiplicative functions. Then one has, of course, the notion of completely multiplicative functions. So those functions satisfy the same relation f of mn equal fm times fn, without, however, any restriction on m and n. So whether m and n are co-prime or not, you have this relation, and then you call such a function completely multiplicative. So for a multiplicative function, it is plain that if n factorizes as the, so Vpn here, this is Vpn. Vpn denotes the power of p dividing n. Power of p, I mean the exponent of p in the prime factorization of n. Okay, so therefore, since the prime numbers are all, of course, co-prime, f of n, if f is multiplicative, splits as the product of the values of f on the individual powers that make up n when written multiplicative. So for all n in n star, you have this relation. Further, if f is completely multiplicative, then since there's no more any condition on this relation, on applying this relation, f of any prime power, so p power k, is exactly equal to f of p the whole power k, if f is completely multiplicative, and of course k is any integer larger than or equal to 1 or even 0, actually. So these are the two absolutely basic notions with which everybody who is attending this talk is completely familiar, I'm sure. And in fact, most people have probably already learned elementary number theory and realized that one of the key questions, basic questions in this topic is to study the behavior of the partial sums of arithmetic functions. So an arithmetic function is simply a function which is just a map from n star to c without any of these additional conditions. So multiplicative functions are arithmetical functions, and completely multiplicative functions are also multiplicative functions. So that's the hierarchy, and I'm sure practically everybody in the audience has studied questions about the behavior of partial sums of an arithmetic function. So you take a real number x larger than or equal to 1, and you sum the values of a given arithmetical function f from 1 to x over all integers from 1 to x. So f of 1 plus f of 2, so on up to f of n, where n is the largest integer less than or equal to x. And the question is, how does this behave as a function of x? One might say that this is the fundamental question that has given rise to the whole subject of analytic number theory. So right from the beginning of the subject, this is basically being the problem to study the behavior of these partial sums for a variety of arithmetical functions that appear in number theory. Halash's theorem, to the statement of which I will get only somewhat later, actually answers this question for multiplicative functions whose values lie within the unit circle. So if a multiplicative function takes values which are all of absolute value less than or equal to 1, Halash's theorem tells you very precisely what the behavior of this partial sum is going to be. So it's a fundamental result in that sense. It answers this question for a large class of functions, namely multiplicative functions whose absolute value is less than or equal to 1 at all elements of n star. So at all it is 1, 2, 3 up to infinity. Okay, so that's what it is. And so you see the question of studying some partial behavior of partial sums is, I mean, in that topic, Halash's theorem is a fundamental result. Okay, so now let us move on to the notion of a mean value. So here is a naive notion of mean value, and that's the only notion that we shall be concerned with. So if f is an arithmetic function for which this limit exists, so the partial sums of f divided by x exists, then the limit as x goes to infinity, then this particular limit is called the mean value of f. It is by no means obvious at all, and in fact it is false, that an arbitrary arithmetical function will have a mean value, because these partial sums can oscillate, and we see that there are obvious and fundamental examples of multiplicative functions or arithmetical functions for which these partial sums are oscillating functions of x, so that these limits, the limit as x tends to infinity, may not really exist. Okay. Nevertheless, if it exists, we call that particular limit the mean value of f. So this is a naive notion of mean value. There are other notions of mean value that are of key importance. You can average in various other ways, but we shall be interested in the simplest notion of mean value, which we denote by m of f. So let me keep track of the time. Excuse me. Yeah. So this is what I shall write as MF in the slides that are followed. Now, having defined the notion of mean value, let me give you the, let's say, practically the fundamental example, the basic example of calculation of mean value. This example may look a little, silly or very easy, but you can confidently say that this is the example that guides the entire, topic, at least around Halash's theorem. All right. So to give you this example, here is what is needed. A simple example. So this is a proposition that I have written here. Let f be totally multiplicative. Again, for simplicity, we assume it is totally multiplicative, and a be a finite set of prime numbers. So this p that I have here, the script p, shall always denote prime numbers in all of these slides. So a be a finite subset of the prime numbers, such that f is 1 if the prime doesn't belong to it. So outside a given set of prime numbers, we are assuming that this totally multiplicative function takes the value 1. Therefore, on all the powers of primes that lie outside this set A, f of p is just going to be f of p power k is just going to be f of p power of k, which is going to be 1. So on all primes and their powers, when these primes don't belong to A, we are assuming that f takes the value 1. Then the mean value of f exists, and it is given by this particular product. It's a finite product since A is finite, and it is given by this product, 1 plus fp minus 1 by p. Okay, so this is a simple proposition. Let us nevertheless see how one can prove this proposition. So here is the proof. The proof uses the devices, which is basically all, I mean, a good part of the, at least the fundamental idea here is the same as the idea that underpins the proof of any mean value thing within the Halasz theorem circle of ideas. So here we go. The proof is to use the convolution idea. So what we do is to consider the multiplicative function h, which is the convolution of the Mobius function with f. So mu convolution f, here mu denotes the Mobius function as usual, and for any p in p and k greater than or equal to 1, we obviously have h of p power k is equal to mu d f of p power k by d, and then all these divisors are just powers of p in order, those all powers of p with exponents less than or equal to k. And since the Mobius function is 0 when you have a number which is not square free, you end up with f of p power, have I written this wrongly? Okay, so it's probably f of p power k minus 1 minus f of p power k. Or is it right? Okay, it seems to be mu of p, which is minus 1. So we have this particular relation. Therefore, h of p for a prime number p is equal to f of p minus 1 when p belongs to A, and 0 otherwise, because for all such primes that do not belong to A, f of p is being set to be 1. Okay? So h of p, which is mu convolution f, is easily evaluated, and its value is given on the prime numbers by these two relations. Also, since you know f is here f of p power k. Oh, I have probably I shall. Okay, yeah. So I should have said that I have assumed my f to be not just completely multiplicative but totally multiplicative, which means, in fact, that yeah, it is totally multiplicative, which is a further notion, which means that its value on all the prime powers for a given prime is equal to the value at that prime. So f of all higher powers of p, so f of p square, p cube, etc., are all equal to f of p. Okay, so that's the assumption I'm making. I'm making these assumptions simply to you know, simplify the calculation and concentrate on the essential point. And therefore, since f is totally multiplicative, we have f of p power k is equal to f of p power k minus 1 when k is greater than or equal to 2. And therefore, you see from this relation that is here that h of p power k is going to be equal to 0 when k is greater than or equal to. Okay, it's not completely multiplicative, that is here, it should be totally multiplicative. Therefore, h of p power k is 0 for all p in p and k greater than or equal to 2. And also h of p is f of p minus 1 when p is in A, and it's equal to 0 when p is not in A. And h is a multiplicative function. Okay. Now, what was the point? I wanted to study how the partial sums of f behave, but I instead started my proof by taking the convolution of f with mu and evaluating carefully the values of this function at various prime powers. Naturally, I propose to relate the partial sums of f to that of h. And that's very easily related by first relating f to h, which is done by the Mobius inversion formula. So here is, so h is equal to mu convolution f, and therefore by the Mobius inversion formula, you have that f is equal to 1 convolution h. Okay. Also note here that since h is mu convolution f, first of all, h is multiplicative, and therefore h of n for any number n is not 0 only if h is not 0 on the prime numbers that divide n, on each of the prime numbers that divide n. And since h is not 0, h of p is equal to f of p minus 1, h is not 0 only for the primes, or only if the prime is an element of this finite set A. So, I mean, h could be 0 even on A, but it's certainly equal to 0 for all primes that do not belong to E. Okay, and therefore there is just a finite set of numbers on which H is not 0. That finite set is the set of square-free integers, all of whose prime factors are in A. So you take A and the set of square-free numbers that come from A. A is a finite set and this FA is a finite set, and H is not 0 only if at all on this set of integers, and on all other integers H is actually 0. Now H is equal to mu convolution F, and by Mobius inversion, as I said, F is one convolution H. And therefore the partial sum of F up to X, which is sigma Fn n less than equal to X, is equal to just by the fact that F is one convolution H, a very standard, I mean just the definition of one convolution H allows you to write that sigma n less than X, sigma d divisor n HD is equal to sigma Fn n less than equal to X. Now one has the absolutely basic, interchange of summation that is prevalent all over analytic number theory, and that is you interchange these two sums. The condition d divisor n is carried now on to n congruent to 0 mod d, and the size of d, since d is a divisor of n and n itself is less than x, d is less than x, and therefore you rewrite this summation as hd summation 1 n over all integers congruent to 0 mod d n less than x. Okay, and what is this sum? It's just the number of so it's just the number of multiples of d less than x, and therefore the sum, the inner sum that we had, this inner sum is nothing but the integral part of x over d. So your partial sum of f has become hd times the integral part of x over d. Remember that hd is 0 except if d belongs to a finite set f of a, f bracket a. Okay, so hd is 0 if the d does not belong to f of a or f bracket a. Yes. Anything?
No, sir. No, you can continue, sir.
Sorry.
Yes,
Right.
Ramana.
So and fa is a finite set. So if you let limit x tending if you let x go to infinity for sufficiently large x, all elements, I mean fa will lie within 1 to x, and therefore this sum can be replaced by d element fa hd integral part of x by d, and then if you divide by x, so you divide here by x and you let x tend to infinity, then for any fixed d, you see that 1 by x integral part of x by d goes to 1 by d for all d, and therefore you just end up with hd by d, d running over the elements f of fa. Here fa is simply the set of square-free numbers that are obtained from the prime numbers, right? So you get this particular thing that this product, since h is multiplicative, you can rewrite this thing as the product p element a 1 plus hp by p, and recalling that hp is f of p minus 1, you conclude that the mean value of f is equal to 1 plus fp minus 1 by p, the product over all primes in A, and this completes the formal proof of the proposition. But more than the actual details, which are in any case very simple, the point is what is the idea used. So we had a multiplicative function, and in order to study the way its partial sum behaves, we instead considered its convolution by the Mobius function, and then worked out the partial sum, then used the inversion formula. So we wrote f as one convolution, a multiplicative function, and then used that to study how the partial sum of f itself behaves, and arrived at this mean value. Now the point is, first of all, this mean value here is written in a way that comes out immediately from the calculation above, but it can be written in a more appealing fashion. And so we do that next. Right. So let's just rewrite the answer. Okay. So 1 plus fp minus 1 by p, which is p minus 1 plus fp by p. This has nothing to do with prime numbers. It's just 6th standard algebra. We just add these things. Rewrite this as p minus 1 by p times p minus 1 plus fp by p minus 1. So you get 1 minus 1 by p plus fp by p minus 1. Expand this as a geometric series, 1 by p minus 1 in a geometric series. You get this 1 plus fp by p plus fp by p square plus so on and so forth. And now recall that f was given to be totally multiplicative. So fp, the fp that appears here can actually be written as fp, f of p square, f of p cube, and so on, because the value of f on all the powers of a given prime are exactly the same. And then you can rewrite the conclusion like this. If f is here, I'm sorry that there's a mistake here. It's f is totally multiplicative and f of p is 1 for all primes not belonging to a finite set of primes. Then the mean value exists and it is given by this product. So it's given by the product over all prime numbers of 1 minus 1 by p plus, times 1 plus fp by p plus fp square by p square and so on up to infinity. Now you see, so therefore for a particular example, which might seem a little artificial, we have found out that its mean value exists and it is given by this elegant looking product. It's a product over all primes of 1 minus 1 by p times 1 plus fp by p plus fp square by p square and so on up to infinity. Now, what were the assumptions on f? F is totally multiplicative. That's a restriction which is a little strong, but that's there only to keep the calculation simple. The second thing was that f must be 1 on all primes outside a finite set. Now, why is this example still interesting? The reason is that one could conceive of approximating any multiplicative function by a multiplicative function which agrees with the given one at a finite set of primes. And presumably for such a function, the approximate function, meaning the one that we use to approximate, will behave like f of this example, and its mean value will look like this as this product. And for that reason, somehow, tending to the limit, one might expect that multiplicative functions themselves should have mean values which look like this. This is
here you don't require f to be totally multiplicative.
No. I'm saying that in my example, I had f as totally multiplicative, and using that fact, I worked out this example. Now I'm trying to use this example as a guide. Okay, so here I'm just speaking intuitively. This is not rigorous, but it will we will make it rigorous shortly. That was the whole idea. So yeah.
In the previous slide.
On the previous slide. Yeah.
I think in this conclusion, last line, this Euler product which you have mentioned, this fp square is fp, right?
No. I was trying to say that my function f is totally
multiplicative, right?
Yeah.
So fp square is fp.
Yeah, that's how I've obtained the conclusion, because
No. So it is not for the completely it is not for multiplicative function.
That's what I said. In fact, that this is an error. The completely multiplicative statement is a slip that I made while writing the slide.
Just
totally multiplicative. Yeah, it should correspond to what I worked out. Okay, so for totally multiplicative functions, I'm claiming that this is the mean value. Okay, now I want to imagine that this works for practically all multiplicative functions. Of course, if I just imagine like this without constraint, I'll make a mistake, and we will see where the mistake lie and then what is the correction to it. But why do I imagine this to be the case? The reason is I can take an arbitrary multiplicative function and then try to approximate it by completely or by multiplicative functions which agree with the given one on a finite set of primes and which are equal to 1 on all other primes. So any multiplicative function you can truncate in this fashion. Okay. Now that resulting function is not totally multiplicative as worked out here, but assuming that somehow this theory extends, so intuitively a given multiplicative function can be approximated by fy, where fy agrees with f on all prime powers, on all powers of prime numbers which are less than y and are equal to, and fy is equal to 1 if p is greater than y. So you fix an arbitrary, you choose a y, and then you can use that y and the given f to approximate, to construct approximations to f in this fashion. Now this fy is of course also multiplicative. That much is there because you can arbitrarily define a function on primes and their powers and use them to create a multiplicative function. That's not a problem. But it is certainly not totally multiplicative in the way I have defined. Nevertheless, one can hope that for these approximations, this result is provable, and therefore by letting y go to infinity or doing something of the sort, one can at least intuitively hope that this mean value works out for all multiplicative functions. That unfortunately is not true. That's not at all true, but still that gives some sort of direction to proceed. So you at least have an idea as to what is the natural candidate for the mean value of a multiplicative function when it exists. It is this nice looking product, Euler product. Okay. So now here is a counter example to tell you that there, in fact, a very fundamental counter example to tell you that mean values need not exist. And the function is, just consider the multiplicative function, which for a given t, real number t, you take f of n to be n to the power I. So this is obviously multiplicative because n times m to the power it is n to the power it times m to the it for any n and m without restriction. So that's not a problem. But its partial sum, unfortunately, just by if you simply replace the sum by the integral, say Euler-Maclaurin formula or integration by parts as you wish, you get that it is x to the power 1 plus it by 1 plus it. It's asymptotic to this. So after dividing by x, the fraction whose limit you want to take as x tends to infinity actually is oscillating with x. It depends on x to the power it. So these limits will depend. I mean, for a given t, you see the x to the power it will oscillate, and therefore this limit won't exist.
Sir, you need t not 0, right?
Pardon? Yes, I mean t is not 0. Otherwise, the mean value will exist, but that's not such a serious problem. I mean, either it will exist for the value t equals 0, and otherwise it will oscillate. Okay. So you see that the mean value, therefore, my hope of proving that the mean value of any multiplicative function is given by this product written in blue is simply dashed by this very fundamental and simple example. But the nice thing, and that is what Halash's theorem says, is that unless your multiplicative function is in some way close to this function n to the power it, n goes to n to the power it, this function, it will have a mean value. Okay, that's what Halash's theorem is going to say. So these bad guys, these functions n to the power it for a given t in R, these functions which are as many as there are real numbers, those are the bad guys for mean value calculation. If your function is not close to a bad guy, then it does have a mean value. And indeed, we will see that the mean value is 0. Okay. So basically, this is what Halash's theorem says, that you expect this mean value to be equal to this Euler product from motivated by a very simple example that you can construct, namely a function which takes the value 1 at finitely many prime numbers and defined to be totally multiplicative. You expect this, guided by that example, intuitively to be the mean value of any multiplicative function. But you see that there are very simple and natural and basic examples of multiplicative functions which don't satisfy this property. But it turns out, luckily, that these are the only bad guys, and that unless a function is in a very quantifiable fashion close to a bad guy, to one of these functions, it does have a mean value. So let's see then how one states this precisely. Before doing that, because this the closeness to these functions NIT will be expressed using a particular condition. In order to motivate this condition, I want to review the method that we use to obtain the mean value of f in the example using Dirichlet series. Okay, so let me review the way we got the mean value using Dirichlet series. So let us associate the Dirichlet series capital Fs, Fn by n power s to the given multiplicative function f. Okay. Now a basic, again, fact in analytic number theory, which again most people would be familiar with if you have gone through a proper course in analytic number theory, in the proof of the prime number theorem and so on, that the partial sums of a multiplicative function are intimately connected to the poles of the corresponding Dirichlet series viewed as a holomorphic function on the complex plane, or a meromorphic function on the complex plane, right? So this is the connection that is exploited in Perron's formula and so on to obtain the asymptotics for partial sums under various conditions. Okay. So now let us suppose that this function, this Dirichlet series has, for simplicity, a pole at 1 plus it. It's not at all obvious that a given multiplicative function's Dirichlet series has an analytic continuation beyond the half plane of absolute convergence and so on. I'm just making assumptions here which are not necessarily true for a given function. Okay. So say partial sums are connected with the poles of f, and let's assume that there is a pole at 1 plus it, where t is a fixed real number, some given real number, and there's a pole at 1 plus it. So capital F of sigma plus it can be written like this, and now I have taken this n to the minus it to the top. So it should have been n to the sigma plus it here, and I have pulled this n to the minus it to the top. So I have f of n times n to the minus it for all sigma greater than 1. Now you will recall in the way we worked out the example, the proposition, we took the convolution of this little f with the Mobius function. We're going to do the analytic equivalent of that, which is dividing by the zeta function, which is the Dirichlet series, the generating series for the Mobius function. So you now let capital H sigma be the Dirichlet series. So here for a real sigma bigger than 1, I'm just now fixing only real values of sigma, H sigma to be f of sigma plus it by zeta of sigma. So this denominator here is the Riemann zeta function zeta. Then since I have divided by zeta, if I multiply it back, I get f. So I can write f of zeta plus it as h sigma times zeta sigma for any sigma bigger than 1. Where h sigma is this series small h by n to the sigma, where h is mu convolution f, like was in the example we saw earlier. Okay, so what's the point of all this? the point is that, okay, you see the Euler product for H is given by this. Now this Euler product, after the second term, so the first term is HP by P to the sigma, second term is HP square by P to the 2 sigma. Since they have these terms all have powers of P greater than or equal to 2, if sigma is close to 1, this part can all be put into something which I have denoted by RP sigma, and which even if you add over all primes, you will get something that extends as a holomorphic function. So basically what I'm trying to say is that this RP sigma contains all those terms whose behavior we can eminently control in the neighborhood of 1. Okay, so what we are left with is only HP by P to the sigma, and capital H sigma is equal to this product. Therefore, if you rewrite this product as exponential of logarithm, expand the logarithm, you can intuitively imagine that you will get H sigma less than, so the absolute value of H sigma is less than an exponential times the real part of HP by P to the sigma. Here I have written real part because in principle the values of H could be complex numbers, and therefore the sum could be actually a complex number. So when you put absolute value of H sigma, your absolute value of the exponential becomes exponential of the real part of the exponent. And HP is FP times P to the IT minus 1, because H is nothing but this mu times mu convolution FT. So you actually looked at the function Fn times n to the minus IT, and you divided it by zeta, and therefore the coefficients of its steady state series are mu convolution that function, therefore HP is equal to this. So the summary of all this is that if you take Fs to be Fn by n to the s, and F sigma equal to H sigma times zeta sigma, you can write your F of sigma like this, where H sigma is mu convolution Ftn. Ftn is the function f of n, n to the minus it, where t is a given real number. And H of sigma, this part, H of sigma is bounded like this. Because, okay, so here there was a small error here. I had forgotten the contribution from zeta. So you see that H of sigma has two. Yeah, so correct. So, okay, sorry, I didn't make a mistake. Yeah, H of P is Fp, P to the IT minus 1, and therefore you get as the real part of H, you get 1 minus real part of Fp, P to the minus IT by P to the sigma. So what is the meaning of...
So summation P RPS, you mean holomorphic in sigma greater than half, no?
Yeah, yeah.
Not 1.
It's a holomorphic on a plane that contains sigma greater than 1.
1
So,
or a half?
No. It's all I need to assume is that it's holomorphic on an open set containing the open half plane sigma. Yeah. Sigma greater
open set containing sigma greater than 1.
Sigma greater than or equal to 1. Yeah. The closed half plane sigma greater than or equal to 1. It should be sigma greater than or equal to 1. Yeah. So I don't necessarily need half. I mean, so I just need to say that the contribution from the RP sigmas is something bounded.
Yeah.
And the point is that your H sigma, which is mu convolution Ftn, therefore is bounded like this. Only the term coming from the primes P figure in this sum here, and you get exponential minus 1 minus the real part of Fp, P to the minus IT, P by sigma. Now, why is this significant? What this inequality tells you is that apart from this factor H sigma, which is bounded like this, F is just zeta. Okay, after translation by T, it's just zeta. So F will have a simple pole at 1 plus IT because zeta has a pole at 1. This relation, because H is bounded in this fashion, provided this series converges for sigma equal to 1. Okay, so you see that if this limit exists, okay, if this limit exists, then using this, you see that H sigma is bounded around sigma equal to 1, zeta has a pole, and one using this pole, one could expect to work out the partial sums of F. Okay, you could work just in principle by something like Perron's formula or so, or if therefore if this series converges at sigma equal to 1, so if this is convergent, then one would expect that for the particular t for which it's convergent, you can expect a relation of this sort for the partial sum of F. But if this series diverges for all t, then you see one may intuitively expect that that divergence will kill the pole here, and your F, the partial sums of F would in the mean go to 0. This is what one would expect, and this is what actually happens. And in fact, Halash's theorem tells you that this is really the case. So Halash's theorem, the specific statement, I mean the precise statement is, suppose F is a multiplicative function which is bounded, so its values are all lie within the unit disk, including the boundary. So F is less than or equal to 1 for all n. If there is a real number tau such that this series converges, then as x tends to infinity, the partial sums of F by x that behaves like this. Okay, and if there is no such real number t, so if for every t real number this series diverges, then the mean value is actually 0. So I'll let you muse over the statement for a moment. It's a very remarkable theorem. You see, it tells you in one shot what happens to the behavior of partial sums of multiplicative functions. Either this series diverges for a particular real number t, in which case the partial sums behave in this fashion. So they have oscillatory behavior. X to the power I tau comes into the picture, unless tau is 0, of course. But x to the I tau comes into the picture, and this is how they behave. Or else this series diverges for all real numbers t, and the mean value is then exists, and in fact the limit is 0. Okay. So this is the statement of Halash's theorem. It's quite remarkable and complete. Of course, you might say it has a serious restriction in that the multiplicative function has to take values less than or equal to 1. That was how the initial thing was stated, and partially several improvements over this condition have been made. On the other side, you can ask what is the rate of convergence here. And these have been answered. So it's the quantitative versions of Halash's theorem that Granville, Soundarajan, Harper have given in their paper on this thing. This, of course, their quantitative version follows a series of various improvements and insights into Halash's theorem that they had been they had obtained over several years. So this is the sort of thing we know now, but not getting into the latest knowledge on Halash's theorem. Let me tell you that the original one is simply dichotomy sort of statement here. Either there's a real number such that this series converges, then as x tends to infinity, you have this, which is what you would expect intuitively from this Euler product consideration. Or else there is no such real number and the mean value is actually 0. And that's basically what we will prove. Okay, so as you can see here, there are kind of three parts to this thing. So first, and as you can see from here, the hard part is to show that if there is no real number such that this series converges, then you see that this series diverges for all t. So then the behavior of this H sigma is no more under control, because you see that the behavior of H sigma was bounded by exponential of that series. It is bounded by the exponential of that series, and if the series diverges, you would want to show actually that H sigma cancels with this, and then the mean value goes to 0. So that's only an intuitive requirement. So you have to actually prove that. That really turns out to be the hard part. So the part or the longer part, at least in the proofs that we have, the longer part would be to show that if this series diverges for all real numbers t, then the mean value is 0. And the next step would be to show that if this series converges, first of all, it converges for only one real number, t. Okay, there can't be two real numbers, tau, rather, for which this series converges. That's quite obvious even from the conclusion here. And then for that tau, you have that the partial sum is equal to this. So there are three steps to execute. The first is to show that if the series diverges for all tau, then in fact the mean value is 0. Then second, if the series converges for some real number, then there is only one. And of course, for that real number, you have this particular behavior. Naturally, from this behavior, from this asymptotic, it is also clear again that this tau has to be unique for the given f, but that will be proved on the way, and then you conclude that this is the behavior if this series converges. So you see, you can use the convergence or divergence of this series. One way of thinking about it is to say that f can be considered close to p to the power, to the function n to the power it, if this series converges. Because the series converging basically tells you that the real part of this fp by, so that's the cosine of, you see, the argument of this particular complex number, and that if the series converges, for most prime numbers, that the cosine is close to 1, which means that this number is close to, fp and n to the I tau are close by in at least as angles, and therefore you think of this convergence of this series as suggesting to you that f and the function n goes to n to the power I tau are close to each other. So one way of intuitively stating this result is to say that if the multiplicative function is close to n to the power it, in the sense that this particular infinite series converges, then its partial sums actually behave like that of n to the it, along with this product multiplied to n to the I tau, along with this product multiplied to it. Okay, but if f is away from all these bad functions, then in fact its mean value exists, and the mean value is 0. So this is the intuitive way, or this is the way that has been, originally it's intuitive, but this has been developed very well by Granville and Soundarajan in their pretentious description, as they said, is functions pretending to be close to some standard function. So this so they've developed this intuitive understanding of Halasz theorem in a very precise and large body of literature, which now guides a lot of topics. So that's where Halasz theorem, of course, has played a very important part in modern analytic number theory. Nevertheless, as a statement itself, it's very nice. Okay, so after this, let's just see what actually motivated Halasz to come to this thing. The original result, which is now a corollary to Halash's theorem, was that if f is a real multiplicative function with values less than or equal to 1, then its mean value exists and it's equal to this product. Okay, where this product is taken to be 0 if it diverges. So this is Wirsing's theorem. Now, Wirsing himself, so after Wirsing proved this, Halasz extended this to complex valued multiplicative functions taking values in the unit circle and obtained this theorem. Now, Wirsing's theorem itself was motivated by a conjecture of Halasz and Wintner, who asked that if f takes only values plus and minus 1, plus or minus 1, then it has a mean value. So this was the question they posed. I think it was Halasz himself and Wintner separately maybe, who posed this question. And this was the one that was finally answered by Wirsing's theorem. Note that Wirsing's theorem automatically, I mean, it obviously includes the prime number theorem in this form, that the average values, the mean of the Mobius function is 0. Where you can plainly apply this theorem to the Mobius function and you get that this is actually 0. So Wirsing's theorem and therefore Halash's theorem is definitely an extension of it's a generalization of the prime number theorem stated in the form that sigma mu n little o of the partial sums of the Mobius function are little o of x. Okay, so the Halash's theorem directly extends that to multiplicative functions that take values in the unit circle itself rather than just real values or values plus or minus 1. Okay, so that is now how does one obtain Wirsing's theorem from Halash's theorem? Okay, so this is actually in fact a simple deduction. Nevertheless, I explained to you the thing. So I want to show that under the conditions of Wirsing's theorem, which is that f is a real valued function taking values of absolute value less than or equal to 1. So taking values in the interval -1 to 1. Then if I apply Halash's theorem to this, I can conclude the fact that it has a mean value given by that product. Okay, so first I have to show that the series that is here, the series in Halash's theorem, diverges for all real numbers t which are not equal to 0. Okay, so if f is real value, then I want to show that for all real numbers t which are not equal to 0, the series in Halash's theorem, so that is this particular series, the one that is written here, this particular series is divergent if t is a non-zero real number. So to do that, let's take A for a given real number t, A to be the set of prime numbers for which the real part of p to the it is less than half. Then 1 minus the real part of fp p to the it is greater than or equal to half. First of all, this number is always anyway a positive number. It's the real part of some complex number which is of absolute value less than or equal to 1. Remember that FPs have values all less than or equal to 1. And FP is real. So real part of FPIT is FP times the real part of P to the IT. So independent of what F is, if I take the set A for which set A to be the set of primes for which the real part of P to the IT is less than or equal to half, then for all primes that belong to A, we have that 1 minus real part of fp p to the it is greater than or equal to half. Therefore, this series whose convergence or divergence we want to study is bounded below by the sum of the primes restricted to just this set A on which this inequality holds. The inequality that real part of p to the it is less than or equal to half. And on A, we have just checked that this is greater than or equal to half. So this series is bounded by half times the sum of the reciprocals of the primes belonging to A. So it's enough to check that this sum, that namely the sum of 1 by p diverges on the set of primes. So if you give me a real number, this has nothing to do with the multiplicative function f. If you give me a real number, t, and I look at the set of primes on which p to the I t has real part less than or equal to half, then the sum of the reciprocals of those primes actually diverges. Okay, so why is that? That's pretty easy to see. If you write the t, the given real number t as 2 pi I theta, then real part of p to the I t is real part of 2 pi I theta log p. So p belongs to the set A simply means that the cosine of 2 pi theta log p is less than or equal to half. And hence p belongs to A only if theta log p lies between n plus 1 by 6 to n plus 5 by 6 for any integer n, right? Because the cosine should be less than or equal to half. So between these two values of n plus 1 by 6 and n plus 5 by 6, this happens. So P belongs to A is equivalent to saying that for the given, for theta, which is t over 2 pi, this inequality is satisfied for some integer. Or taking exponentials, this means that it is satisfied for prime. So if P is less than or equal to, greater than or equal to this, and less than or equal to that. So you just for compactness, just for brevity, we write an to be e to the n plus 1/6 times theta. So you see that the sum of the reciprocals of the primes between an and this constant times an can be bounded like this. So you just multiply a log p and divide by log p, and then take the bound on the upper end point, and then sigma log p you bound. Okay, so sigma log p is bounded by essentially lambda of n in this range, and so this sigma log p is bigger than let's say some constant times an. So the an cancels with the an here, and you get a log can, and an is exponential of n plus 1 by 6 theta. So you get n plus 1 by 6 theta here. And if you put that in the reciprocal, you get the harmonic series, and you see that the sum of primes, reciprocals of these primes diverges. All that's needed for this calculation to go through is the fact that sigma lambda n between summed over integers of this sort for a given constant is greater than. This is not, doesn't need P and T. Remember that doesn't need prime number theorem, because I'm saying that I'm going to use this in deducing Wirsing's theorem from Halasz theorem, and I claim that Wirsing's theorem contains the P and T. So I don't want to engage in a circular argument. This is a lower bound that you can get from a Chebyshev type bound. So with that, you end up by showing that this reciprocal of primes diverges. Once you know that this reciprocal of primes diverges, you conclude that this particular series diverges for all t which are reals but not zero. And therefore, if you apply Halash's theorem, you will conclude thus Halash's theorem either holds for, so the condition holds for either tau equals 0 or condition B holds. So either that series diverges for tau equal 0, or the mean value of f itself is 0. Thus, either you have this, either this series converges, I mean for tau equals 0, so you have this series converges, and we have this as the behavior of the partial sums, or we have that the mean value is 0. But we wanted to show that a real function which takes values between -1 and 1 always has a mean value, not a conclusion of this sort, that this partial sum behaves like this, you see, behaves like this, or that this is 0. So the second part tells you that it has a mean value, but to extract the fact that it has a mean value from this, I need to still show that as x tends to infinity, this series, this product converges. So basically what I have to argue is that if this series converges, then this product converges. If this series diverges, then this series diverges, and its value can be taken to be 0 in that case. So that's just a question about, series, the relation between series and product. So you write this product like this, and you see that the main contribution comes from FP minus 1 by P. So you want to assert that if you can write a series like this, where UP is FP minus 1 by P, VP is of this sort, and we see that UP square is square summable, VP is just summable, then this product converges or diverges as UP. Okay, so once you have this relation between product and series, you conclude that the mean value always exists. So let me just repeat this thing here. Using Halash's theorem, we conclude that the partial sums of f divided by x either are asymptotic to this function of x, or else they go to 0. We want to say that this product of primes up to x has a limit as x tends to infinity. So we want to claim that this product converges if this series converges, or else we want to say that this product diverges and it can be taken to be 0. So combining both, you end up with Wirsing's theorem. Okay. Therefore, you only need some statement that tells you relation between products and sums, infinite products and infinite sums. This is it. So this is some very basic mathematics. I don't deny at all, but it often enough, at least if you're me, you can start looking for various conditions that will nicely tell you that these things work properly. So one such thing is a lemma which is in Tannenbaum's book, which I am quoting for you, and which is what I've used. And if you use this lemma, you immediately then conclude Wirsing's theorem from Halash's theorem, provided you go through the argument about the series diverging if t is not 0. So here is this simple lemma. I will actually prove this lemma in the next lecture, simply because this very elegant and simple lemma is extremely useful in arguments about products and sums, which we will repeatedly use in the at least the last part or the key part of Halash's theorem. The proof will involve using explicitly this lemma. So I'll give the proof, which is completely given anyway in Tannenbaum, but nevertheless, for the sake of exposition, I will explain the proof in the next lecture at the beginning. But here is the lemma for you to see. This is just a statement about products and series, has nothing to do with analytic number theory of any sort. I mean, it is applied, but not to do with it. So you take, suppose H is positive, UN and Vn are complex numbers, and 1 plus UN plus Vn is not equal to 0. Then if the UN is L2 and Vn, which is viewed as some sort of perturbation on UN, is L1, so you have this condition on UN and Vn, okay, and that their sums L2 plus L1 is less than H, then first of all, this product converges or diverges as this sum. So you just check that you can write your product as 1 plus UN plus Vn, Vn in L1, UN in L2, then you are confident that the product converges or diverges as the sum. Moreover, you have this very neat explicit estimate that 1 plus the product 1 plus UN plus Vn is less than exponential 6 times this H that comes here plus the sum of the real parts of it. Okay, so this is the lemma from Tannenbaum. I've given you the precise place where it appears. In fact, just before Halash's theorem is where he quotes this, proves this lemma. And with this lemma put in, you can conclude from Halash's theorem the two conditions that you get. Both imply in Wirsing's situation that the partial sum exists and it's given by the product. Okay, so I think I will stop today's lecture. It's exceeded 1 hour. Okay, yeah. So I think I'll stop today's lecture here and resume first from a proof of this simple lemma, which has nothing to do with analytic number theory. And then I will go into the steps of the proof of Halasz theorem, as I mentioned. First, proving that if the series diverges for all t, all tau, then in fact the mean value exists and it is 0. This is the longest part. It will take a few steps to do. Once I'm done with it, I'll prove that if the series converges for some tau, it converges for a unique tau. That I have practically proved except for a small observation. I've proved it already implicitly in what I have said. Once that is done, and that's a very small part, then I will finish the last part, which is to show that if it converges, then the mean value behaves as stated in Halash's theorem. So that is that. Thank you very much.
Thank you very much for this nice take off to this topic. And are there any questions? Saurabh, you should check the chat box or anything.
No, sir, there is no question in the chat box.
Okay. So the next talk will start at 4 o'clock, right?
Yes, yes.
So
Okay.
if people did not follow, because this is supposed to be fairly instructional, right? This part of the thing. No, hello?
Yes.
Yeah, this is supposed to be instructional. So if people didn't follow, please feel free to write to me so that I can respond, or please raise the question as you have the next time. Okay.
Okay, thank you very much. And the next talk we will resume at 4 o'clock.
Right. Okay.
Okay.
Then we will meet at 3:55. Sir.
Yes. 3:55 we meet. Thank you very much.
Thank you.